Today we're going to talk about partial fraction decomposition, which is a way to allow us to integrate problems that don't work with U substitution or any other method of integration that we've learned so far. So this is the last new type of integration that you're going to learn. So what we're going to do is we're going to break up a fraction into its parts. So I'm always going to factor. I have to pay attention that the numerator is a smaller degree than the denominator. If it's not, I have to do something different, which we'll talk about later. So since it's linear on top and quadratic on the bottom, I can just go ahead and factor. So I have x plus 5 over x plus 2 times x minus 1. Now what I know is that likely that x plus 5 over x squared plus x minus 2 came from two different fractions. It came from a fraction with x plus 2 and x minus 1, and I did maybe added them together. There was something on top and something on the bottom to get x plus 5 over x plus 2 times x minus 1. Since the degree on top is linear and smaller than the degree on the bottom, I know that the numerators of the two separate fractions have to be 1 degree less than what's in the bottom. So these are both constants on top, so I'm just going to call them a variable. I'm going to call that capital A and capital B. And I'm going to multiply the entire equation by the least common denominator of x plus 2 times x minus 1. So when I do that, the x plus 2 factor cancels with the x plus 2 factor in the first term, so I just have A times x minus 1. In the second term, the x minus 1's cancel, and I'll have b times x plus 2. On the right-hand side, the whole denominator will cancel, and I'll have x plus 5. Now really, what I have here is three separate variables that I need to solve for. Well, I'm not really solving for x. X can be anything I want it to be. I could put 1 in for x, but 1 doesn't, well actually 1 does help. I could put 0 in for x. 0 doesn't really help me because it doesn't get rid of the x's. It doesn't get rid of a or b, it gets rid of only x. So I have to get rid of two variables in order to solve for the third. So like, if I let x equal 1, then the a term is completely gone and I can solve for b because I will have taken care of x and b will be the only variable left. So if I put 1 in for x, a is gone, I get 3b equals 1 plus 5 is 6, so I get b is 2. Again, if I pick conveniently negative 2 for x, the b term is gone, and I would get negative 3a equals 3, so a is negative 1. So what I'm then saying is that this fraction that I started with, x plus 5 over x squared plus x minus 2, is really, it came from negative 1 over x minus 1 plus 2 over x minus, a is over x plus 2. It's negative 1 over x plus 2 and 2 over x minus 1. And if you don't believe me, let's get a common denominator and do that fraction. So I'd have x plus 2 times x minus 1. The first term would be missing the x minus 1, so it would be negative 1 times x minus 1. The second term would be missing the x plus 2. So when I multiply out, I get negative x plus 1 plus 2x plus 4 over x plus 2 times x minus 1, which is x plus 5 over x plus 2 times x minus 1. So all I did was I found the components of the fraction x plus 5 over x squared plus x minus 2 that it broke up into. Well, that helps us because if I'm asked to integrate x plus 5 over x squared plus x minus 2, if I let u be x squared plus x minus 2, then that means my du would be 2x plus 1. There's no way for me to change 2x plus 1 into x plus 5. There's no way for me to manipulate that. So instead what I do is I say, okay, well this fraction, x plus 5 over x squared plus x minus 2 dx, is really the integral of negative 1 over x plus 2 plus 2 over x minus 1 dx. And now I know how to integrate that, because that's really just something to the negative 1 power, which becomes a natural log. So that'd be negative natural log absolute value of x plus 2 plus 2 times the natural log of the absolute value of x minus 1 plus c. So while I couldn't integrate this problem in a different way, I was able to break up the fraction to allow me to integrate. Let's look at another example. So, is the degree on top less than the degree on the bottom? Indeed it is. So let's factor the top and the bottom. Well, the top doesn't factor. The bottom factors into 3x times 3x plus 1 times x minus 2. Maybe just make sure that's right. Yep, that's right, dx. So I'm going to go over here, and I'm going to say, okay, 1 minus 3x over 3x plus 1 times x minus 2 can be written as something over 3x plus 1 plus or minus something over x minus 2. So I'm going to call that a and b. And I'm going to multiply by the least common denominator again. So on the left, I just have 1 minus 3x. On the right, I would have a times x minus 2, and on b times 3x plus 1. Okay, picking conveniently for x. Let's see, if x equals 2, that would be get rid of the a term, right? So 1 minus 6 is negative 5. 6 plus 1 is 7, so I'd have 7b. So negative 5/7 would be b. B's a little yucky to get rid of. X would have to be negative 1/3. But if I put negative 1/3 in for x over here, I get 1 plus 1, or 2, equals negative 1/3 minus 2, so negative 2 1/3 a, which is really negative 7/3 a. So that means that negative 6/7 would be a. So my integral, instead of being negative 1 minus 3x over 3x plus 1 times x minus 2, that now becomes the integral of negative 6/7 over 3x plus 1 minus 5/7 over x minus 2 dx. Well, that might not look much better to you, but I can bring those constants out front and separate the integral. So I could say that's just negative 6/7 times the integral of dx over 3x plus 1 minus 5/7 times the integral of dx over x minus 2. Well, I know that I get a factor of 3 from 3x plus 1 when I integrate that I don't have in my dx. So I need a 1/3 out front. So that means that that's really negative 6 over 21, or negative 2 over 7, times the natural log of the absolute value of 3x plus 1, minus 5 over 7 times the natural log of the absolute value of x minus 2. Don't forget your cupcake. Okay, hopefully that doesn't look too bad to you. All right, now we get into things that can be a little more difficult. So, when I factor this next problem, I know I have dx over x minus 1, because that's already there for me, and that would factor into x plus 2 times x plus 2, which I could write as x plus 2 squared. So, how do we know how to set this up? Because x plus 2 squared is really a quadratic. We don't call that a quadratic in this case. We call it a repeated linear factor, because I could conceivably have 3 fractions, something over x minus 1, plus something over x plus 2, plus another something over x plus 2, and the common denominator would be that. Or I could have something over x minus 1, plus something over x plus 2, plus something over x plus 2 quantity squared, and that would have the same denominator. Or I could have something over x minus 1 plus something over x plus 2 squared. And I don't know which one of those cases I have, but this middle case takes into account everything that's possible. So we're saying that this term here is a repeated linear factor, so we're going to put a constant on top. So what I mean by that is whenever I go over here to the right, and I rewrite this as 1 over x minus 1 times x plus 2 squared, then I'm going to say that's a over x minus 1 plus b over x plus 2 plus c over x plus 2 squared, because that's this case here where I'm allowing for everything to happen. So multiplying through by the least common denominator, I get 1 equals a times x plus 2 squared plus b times x minus 1 times x plus 2 plus c times x minus 1. Well, I know that if x is negative 1, I'm going to be able, if x is positive 1, I'm going to be able to find some stuff. So if x equals positive 1, I will get 1 equals 1 plus 2 is 3. 3 squared is 9a. The b term and the c term drop out, so a is 1/9. If I put x equals negative 2 in, then the a term will drop out, the b term will drop out, and I'll be able to solve for c. So I'll have 1 equals negative 3c, so c is negative 1/3. The problem is, at this point, I have no way to get b to be able to solve for b. So what I have to do at this point is plug in my a and c. So 1 equals 1/9 times x plus 2 squared plus b times x minus 1 times x plus 2 plus c, I don't want c, I want negative 1/3, so minus 1/3 times x minus 1. So I only have one variable plus an x. So I can let x be whatever I want it to be. I'm not trying to get rid of the b term, I just want to solve for the b term. So convenient value of x would be 0. So if I say 1 equals 0 plus 2 is 2 squared is 4, so that'd be 4/9, plus b times negative 1 times 2, and 0 minus 1 is negative 1 times 1/3 times negative 1/3 is positive 1/3. So what I end up here with is, let's see, this is really 3/9, so that'd be 7/9 minus 2b equals 9/9, because that's 1. So really 2/9 is negative 2b, so b would be negative 1/9. So I've used up a lot of my space here, but let's see if I can fit this in. So this fraction becomes a, which is 1/9, so 1/9 times the integral of dx over x minus 1. b is negative 1/9, so minus 1/9 times the integral x plus 2 dx. And c was negative 1/3, so minus 1/3 times the integral of dx over x plus 2 squared. So when I integrate the first one, I still have 1/9 natural log absolute value x minus 1. Second one, negative 1/9 natural log absolute value x plus 2. But when I integrate this next one, if u is x plus 2, it's actually u squared in the bottom, so it's u to the negative 2. So that becomes a negative u to the negative 1. So that becomes a plus 1/3, and I would still have x plus 2 in the denominator. Don't forget your cupcake. Okay? Now I realize that this is more confusing and more complicated, so we're going to do another example like this, and then we're going to stop our notes and practice some of these before we introduce other types. So my last example has a typo in your sheet, and that it should be 2x squared on the bottom of that particular term, that middle term in the denominator. So the first thing I'm going to do is factor the top and the bottom. Well, the top doesn't factor, but the bottom does factor. I can factor that into, let's see, I'd have 5x squared plus 20x plus 6. On the bottom I can take an x out, so I'd have x squared plus 2x plus 1. Oh, well that factors into x plus 1 times x plus 1, or x plus 1 squared. So I have 5x squared plus 20x plus 6, forgot my dx, that I'm trying to integrate. So again, I have a repeated linear term. I have an x plus 1 and an x plus 1 squared. So when I go over here to the right, I start with 5x squared plus 20x plus 6 over x times x plus 1 squared. So I have three fractions, a over x, b over x plus 1, and c over x plus 1 squared. When I multiply through by the least common denominator, I just have 5x squared plus 20x plus 6 here. On the right, I will have a times x plus 1 squared plus b times x plus 1 plus c times x. So I know I can let x equal 0, and that gets rid of the c and the b and lets me solve for a. So if x is 0, I just get 6 equals a, because 0 plus 1 is 1, squared is 1. If I let x equal negative 1, I'll get rid of the a term and the b term. So I'll have negative 1 squared is 1 times 5 is 5, minus 20 plus 6 equals negative c. So I have 11 minus 20 is negative 9, I believe. 11 minus 20, yes, is negative 9 equals negative c, so that means c is 9. Again, I have no way to get rid of b, so I plug those values in. So I say 5x squared plus 20x plus 6 equals 6 times x plus 1 squared plus bx times x plus 1 plus 9x. So if I let x equal 1, I can solve for b. So I'll have 5 plus 20 plus 6 is 31 equals 1 plus 1 is 2, 2 squared is 4, plus 6 is 24, plus b times 1 is b, times 1 plus 1 is 2, plus 9. So 24 plus 9 is 33, plus 2b equals 31. So negative 2 is 2b, b is negative 1. So really I'm now integrating the problem of a over x. So a is 6, so 6 over x. B is negative 1, so minus 1 over x plus 1. And c is 9, so plus 9 over x plus 1 squared dx. There's really no reason to rewrite this one because it's not fractions or ugly, so I can just go ahead and integrate. So I know that's going to be 6 times the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 plus 9 over, because that's actually u to the negative 2, actually it would be minus 9 because it's u to the, when I integrate u to the negative 2, I get u to the negative 1 over negative 1. So times x plus 1, and then plus my cupcake. Okay, that's almost 20 minutes. That's as far as we're going to go today. In class tomorrow we will practice some of these, and then we will have notes on the next version of partial fraction decomposition.